Hello, AP Stats. This is Mr. Kim with the Chapter 10 notes present here before you guys. I know that for the upcoming week, you'll be more stressed about the Chapter 9 test. And this is going to be a very quick lesson through Chapter 10 stuff, mostly about the T distributions and going over Chapter 11 during the school, but Chapter 10 I would like for you guys to learn on your own. It's very simple. Have to just learn about what T distribution is, when to use it, how to use the calculator for, and all that good stuff here. Chapter 10 is just all about what we call estimating means with confidence. So we're involving a confidence interval back into our play. And it's no longer going to be about null and alternative hypothesis. It's still going to be now going back to 99%, 95%, and those type of things. But with T interval, not a Z, but T. And I'm going to go over what the T samples mean, T test, what all those things within this chapter here. All right, so the T distributions, if you take a look in the formula sheet of the standard AP test exam for stats, there was this table full of values for Z-scores, right? And that was the first 2 pages of the whole bunch of decimal values. And the next 2 pages, and it turns out to the last, maybe the 3rd and the 4th one, I think, which is the last pages of the formula sheets, they will have something called a T distribution critical values. And they have all of these values in which it pretty much calculates the probability or the values themselves at certain percentages. And if you notice on the left-hand side, we have this thing called DF. And on the right-hand side, well, it doesn't really label it for you, but I'll go over what DF means in more detail. It's called degrees of freedom. Okay, and all of these values that we have in terms of the probability up there. So you're talking about the top 25%, 10%, all this stuff. What value are you standing at when it comes to those things? Okay. So what are T distributions? So T distribution is pretty much the same thing as a Z distribution, except that it allows for a wider range of, let's say, the values to capture. So there's a little bit of a simulation that I would like for you guys to see. And this is also from the textbook. If you guys were to, let's say, use something like this, where the Rossman chance applet collections, I'll leave the link for you guys in the chat there. So this is a Rossman chance applet collection where we can kind of play around with the values and see the main difference between the T distribution and what the Z distribution is about. And so it's going to give you all these little confidence intervals once we put in some, just input. So I'm going to put statistics here as means. We're going to have distribution with normal and Z with sigma. So this right here, Z with sigma, means we have a normal distribution with a standard parameter, which is standard deviations. Population mean, I think from the textbook also with the description they provided for us, I'm going to just type this in as 100, and population standard deviation, I'm going to type in as 20. And then for sample size, we're going to make this into a 4. And then for the number of intervals, we're going to make it into 100. Okay, and then when we press sample like this, now notice that these dots all indicate how much the samples app actually captures a true mean. So you can see that on the right, there's only one red little line, which means that was the only sample that have actually failed to capture the true mean within the sample confidence interval. Now our confidence interval was about 95%. And so with the next couple of examples, I'll show you that pretty much there's going to be a lot more descriptions or the difference between what Z with sigma would be and what Z with without a sigma, or T and Z with S, which is stand for sample standard deviations, not the parameter. And so let me make the confidence interval to actually be about 99% instead this time. And so your confidence interval is actually going to get a lot wider. And then I'm going to just press recalculate. And now notice how pretty much everything is it's captured, right? All the samples here, everything is going to be captured because our confidence interval is very wide enough. And that's how all the samples that we've taken they're all going to capture this population samples here. And now what we're going to do is we are going to reset, and we are going to simply just keep Z with S this time. Instead of saying sigma, we're actually going to do Z with S. And let's see, then I'll change the number of intervals to 50 and press sample 20 times, more than 1,000. Okay, so instead of saying 100 samples, let's try to just make this a little bit smaller and make this, let's say, a 50. All right, now I'm just going to press sample here. Now, notice what happens is that even though at a 99% confidence interval here, we have several times where we're not going to have the true mean captured within the confidence interval. And the reason for that is because what Z with S stands for is a sample standard deviation. A sample standard deviation is not reliant enough. It doesn't really give you a true parameters, which is a standard, true standard deviations of the distributions. Now, if you don't have that, if you just have a sample standard standard deviation, it's not actually going to be very accurate though. Anytime when you're taking more samples, taking a population parameter, it's going to be much more accurate, and rightfully so, because if I were to take a mean of everyone in the school district, then it would represent everyone in the school district. But if I only take a small sample of it and took statistics with it, then it's not really going to be a good representative of the entire thing. It's the same situation here. So if I use Z with S versus, let's say, Z with sigma, and just let's say sample again, it's going to give you a lot more instances where the confidence interval will capture the true mean here. And I am going to simply just keep on doing this here with simple S and then try to see. And notice how now, like with Z with S, it's going to be 3 times. This is like more than 3 times. You can see that there's going to be 6 lines here. So in all, sample standard deviation is not a good thing. It doesn't accurately measure up to the true distributions. It's not going to capture the true mean so well. So what do? We use something called a t distribution to actually counterbalance that. Now, what t distribution is, as you can see from this description, is that it's wider than a normal curve, and it's with captures a greater uncertainty when using standard sample standard deviation, instead of using the actual sigma. So whenever we're faced with situations where we only are given a sample standard deviation, we want to use t distribution so that we can actually capture within the confidence interval that's given to us, so that we can capture a lot more, so that the true mean does fall under. And if I keep on pressing sample, look at how wide the confidence intervals are for some of these things. Now, I know that there's this one red up here, but compared with Z with S, I know for a fact that it's going to be able to capture a lot more with a t distribution, just because it's that much wider here. Okay, so in a nutshell, that is what it is. And the degrees of freedom basically is how much sample size you're given. Remember, the degrees of freedom is n-1. The more sample size you have, the more degrees of freedom you're going to get. So the more samples that you have, the narrower the t distribution will be, which means more data will be centered around the true mean and much more accurate in measuring certain things, such as calculating the probability of, and within the confidence interval, how much is it going to capture, and all of those things. And we'll try on some of these problems as we talk about the next couple of slides here. Okay, so that was the basic concept of t distribution. And again, for the conditions for constructing a confidence interval about a mean, you've seen this before already. We're going to check for randomness. We're going to check for the independence. This is only when if you believe that there's enough evidence to believe that it's not going to be independent, then you can use the sample size is less than about 10% of the true population number, and then that can prove your independence. Normal S/large sample here, we're not going to be able to use n times p or any of that sort, because you're not going to give any proportions or probability of any sense. Rather, you're going to be using the central limit theorem that states that as long as I have a large enough sample, which is greater than or equal to 30, then we can pretty much assume that this will be a normal distribution. So if on a question on the AP statistics exam asks you to construct and interpret a confidence interval, all the conditions should be met. you are still required to state the conditions and show evidence they're met. So including a graph if the sample size is small and data are provided. So make sure that whenever they ask you to construct a confidence interval, that you check the plan part, you check for all those conditions before you're moving on to the do and the interpretation portion. All right, so the one sample t interval for a population mean, this is something that I would like for you to write down in your notebook. So whenever we're constructing a C% confidence interval, this is going to be your, I would say the critical value, right? The t, actually, I'm sorry. The critical value usually comes from the fact that this is the t value. Those are the ones that's actually called the critical value. I have to double check on the vocabulary up a little bit, but what this actually is that this is your standard deviation. It's very similar to the ones you've seen before with a margin of error, basically. The plus and minus t times the standard deviation over square root of n, that is plus and minus. So it gives you the higher and the lower boundary. So your interval from this to that captures the true mean. There was another word for this. I'm just going to call this sample mean for now, because obviously that's what it means. And this is the critical value, the t. That is in a t distribution, where do you lie? I mean, what is that value where on the t distribution where you stand, in which you can multiply by the standard error of statistics and then get the confidence interval left to right. T star is the critical value for the t distribution with n-1 degrees of freedom and C% of the area between negative t and positive t. All right, so the next slide, we have a problem. You learned that 73% of Americans claim to have read a book in the previous 12 months. This was based on a 2016 Pew Research Center study that interviewed a random sample of 20 American adults. The same study also reported that the average number of books read by the members of the sample was the mean of X is 12, or sample mean is 12, with a standard deviation of sample standard deviation being 18. Now remember, no mu, no sigma is used. We know now that we're dealing with samples. Okay, so if we're dealing with sample standard deviations and not really the standard deviation of the parameters, that means that we actually have no choice but to kind of think about it in terms of t distribution case. So construct and interpret a 95% confidence interval for the mean number of books read by all American adults in the previous 12 months. So whenever you're doing this, we're going to be using this formula here that says mean of X plus and minus t star, the standard deviation over square root of n. Now the t is a critical value for the t distribution with n-1 degrees of freedom. Okay, so the mean of X was 12. So the n is equal to 1520 here. And so the degrees of freedom will be 1519. Right, and so after that, what's going to happen is that when we're constructing a 95% confidence interval, we actually have the percentage to be 0.95. What we can do is we can actually pull up a calculator, and I'm going to show you this right away, and so that it kind of saves us some time as to how to calculate this. So on your calculator, if you actually go to second VARs, and there's going to be TPDF and TCDF, as you can see. All right, so here's how we're going to be able to do this very quickly by using the calculator. So it's t intervals here. When we go, we're going to be asked to input the stats because we're all given that. So we have a standard. Oh, I think I'm in the wrong thing. So we're going to go to t interval. All right, so we're going to go to stats. So everything that's given to us, such as the mean of X, the sample standard deviation, well, we're going to just type them in. So 12 books and then 18 books here, and n was 1520. And confidence interval is 0.95. When you press calculate, and then it's going to give you these two numbers, 11.094 and 12.906. So what this means is that we are 95% confident that between 11.094 and 12.906, that captures the true mean of I would say the number of books that the average American adults have read in the past 12 months. And so that is how you would construct and interpret the 95% confidence interval. But of course, planning and doing planning, let's check for the conditions here. So to check the conditions, we have randomness, random sample, check. Do we have enough reason to believe that there's more than 1520 or 15,200 Americans out there? Yes. Population is well over a couple hundred million. Is there enough reason for us to believe that n is greater than or equal to 30? Yes, the central limit theorem that allows us to assume normality. So everything's checked off. So plan part is checked. State, what are we doing? We are constructing a one t-test, I believe. Yes, so we're constructing a confidence interval for the true mean of the number of books read by all American adults in the previous 12 months. That is always you start with a confidence interval, 95% confidence interval. We're constructing that for the true mean of all the people, or the mean number of people who read American American adults who read a book in the previous 12 months. That's what it would say. So that will check. And I told you what the plan part would be. And for this one, when we actually do this, we need to find out the t-star value, and that is going to get a little tricky here. But what we do is, in order for us to find the t-value, we have to use a table, or you can use a technology. So when you actually go to second VAERS, and when you do inverse t-value, I believe, the area is 0.95, and I believe that most likely the degree of freedom is 1519, and when you press paste, gives you about 1.64. So to use the technology here, I know that the t-star says 1.962, and here's a way that you guys can figure this out. Now, one of the ways is that you can use the table on the formula sheet, and the 1.962 will be the value for I think the confidence interval, which is the percentage, to be about 0.975. Now, there's a specific reason as to why are we using 0.975 when the confidence interval clearly states that it's 95%. And this is how you always want to think of it. Remember that the confidence interval always starts from the middle, not from the left. So if the inside is 95%, you must always consider what is this value at the most right-hand side when we're considering the inside to be 95% plus this little extra that you can figure out because it's symmetrical. Now, the rest of these two should add up to become 5. Half of 5 is 2.5%. Therefore, this line, wherever that t-star value should be, it's about 0.975 from the left all the way towards that line. And that is the area that you're going to plug in. Sorry, my calculator is just lagged out, so I'm just going to pull it up once again. So here's what you're going to do. You're going to go to second VAERS. You're going to go to inverse t. They're always going to ask you for two things. So for area, you're always typing in the confidence interval area, which is 0.975. And the degrees of freedom is always one less than the sample. Now, I know that the lowest or the highest number on the table goes up to is 1,000. So anything that's well above 1,000 or even maybe a couple of hundred, you're always going to just use 1,000 and that should be good. So degree of freedom is 1519, whether you use a table or when you use the technology to do this, your t-value, as you can see, should say 1.962. Now, obviously, if I was in class, I would show it to you guys. Hey, this is how you would do it. Plug in all those numbers. Now, everything else is given to you. The sample mean, the sample standard deviations, and the sample size. Plug everything in, and you will eventually find out that the confidence interval is going from 11.09 to 12.91, which is exactly the same thing that we got by using the calculator, which is way up here. Okay, so interpretation. I'm just going to show it to you right away. We are 95% confident that the true mean of the number of books that the average American adults read in the previous 12 months will be captured by the interval between this to that. That is something you would say. So from interval that to that captures the magic word is the true mean, the number of book read by all Americans the previous 12 months. So same thing as before, going back to chapter 8 when we talked about the confidence interval, just copying and pasting it. Really what chapter 10 is all about is this new thing called t distributions. Quite honestly, that's pretty much it. Okay. Now, part B, 2011, Pew reported that adults read an average of 14 books. Does your interval part A provide convincing evidence? I don't believe so, because 14 is way off the mark. I mean, it's not even part of the confidence interval, so we're not really confident. We're not really sure that that data is accurate. I'm sorry, is 14 within the interval? Oh, I'm sorry. So 14 is not in the confidence interval, so 14 is not a plausible value. So there you go. So it's not a mean number read in the previous 12 months by all Americans. So is there enough? Oh, I think this is the question. Provide convincing evidence the mean of all Americans of 2016 is different than 14 books. Explain your answer. Yes. So 2011 compared to 2016 is obviously going to be different. Okay, so for this, we have basically a sample of manufacture of high resolution video terminals must control the tension on the mesh of fine wires that lies behind the surface of the viewing screen. So here are the tension readings from a random sample of 20 screens from a single day's production. Construct and interpret a 90% confidence interval. What I would like for you to do is just pause the video right now and just think about what you must do in order for you to solve this question. And just write it down, construct, and do all the necessary steps: state, plan, do, interpret. And once you're ready, just play it back and then check your answers over. Okay, so assuming that you guys have finished it, I'm going to first start with the state. We are constructing a 90% confidence interval for mu, which represents the mean tension of all screens produced on this particular day. Now, when we plan, we're planning to do one t-test for interval, or we just call it one t-test interval, and somewhere along those lines, I believe. I think the exact words that they like for you to use here is actually it's actually up here, one sample t interval for mu. So I think I said it was one sample in one interval. Sorry, one sample t interval for mu. Okay, so that will be a much more accurate way of saying it. But that is something that you just say it for what type of test you're going to be doing. Random, 10%, as well as the n greater than or equal to 30. First of all, we don't have a sample that's greater than 30. So that's going to be a problem. So, but we are still going to assume normality for this. And I believe that it says here, the dot plot does not show strong skewness or outliers. So this is something that's actually different from the other chapters, is that even though that the central limit theorem states that it has to be bigger than or equal to 30, when you guys actually look up here, if the population distribution has unknown shape and n is less than 30, use a graph of the sample data to assess normality. So if you use a dot plot to actually distribute the entire data set and see if it actually does not appear to be too much of a skew, then we can assume normality for that type of problem, and then we can actually move on. So going back to this, we do not have enough sample, so it's less than 30. So what do? We're going to put them on a dot plot. So here, obviously I'm not going to sit here and just like put all the dots for you, but this is a good enough reason to assume normality because there's no strong skewness to left or right. Most of the data is congested to the right, right in the middle. So that's a check. 10% of all the screens from a single day's production. The tension readings from each of these samples, I believe they're going to be independent from one another. As long as it's a random sample, which is a check, I believe this should be all good. So here, if you take a look, 10% of student 20 is less than 10% of all video terminals produced that day, which is a check. And so that is the state plan portion. Now let's do the do. And I am not going to sit here and work on it by using the inverse t. I'm simply just going to go to stat test. We're going to go to t-test. Well, I'm sorry. So for this t interval, sorry, we're talking about a confidence interval here. So the mean and sample mean of the sample standard deviation, unfortunately, it's not really stated, and C level is 0.90. So we have no choice but to go to stat and edit. We're going to put all of these things individually, 297 point. And then 269.6, 283.3, 304.8, 280.4, 233.5, 257.4, 317.5. Okay, so we have the 20 samples, and then now you guys obviously know cap one variable stats. When you do that, it gives you really nice numbers with the sample mean of being 306.32 and a sample standard deviation, which being 36.209. Remember, we want to be using those values, not the sigma, which sigma means it's going to actually give you something less than a degree of freedom. So we're going to be using those values, and I believe we actually have those values intact. So we're going to be using the now copying and pasting those numbers into our stat test for T interval test. Oh, wow. So they actually just put those values in right away for you guys once you do that. So calculate that. And there we go. So we have between 292.32 and 320.32, just like how our answer key says. Now we all should know how to interpret this. I'm not going to write it down for you, but we first start off with we are 90% confident that the interval from 292.32 and 320.32 captures the true mean of I think the mean tension of all the screens produced that day. So that is here, as you can see, 90% confidence that the interval between 292.32 to 320.32 captures the mean which we stated at the very beginning for the state portion. Okay. So it is not enough just to make your graph of the data on your calculator when assessing normality. You must sketch the graph on your paper. So yes, that is a bit of a pain. However, that is a way to demonstrate the fact that, hey, we're not going to have a skewed graph, just this dot plot right here. On the free response questions or any of that sort, just make sure you guys plot that. Just try to copy it quickly as possible to prove of the normality when your sample size is less than 30. I've already showed you guys how to do it. T interval, that's what you would do. And for this type of question here, I'm going to just first ask you guys to pause the video again. And once you're done, please check it over. Okay, so sorry I skipped a little bit of the video here. I basically have gone to put the state portion and the plan portion. As you can see, state is just 95% of the confidence interval for mean healing rate in micrometers. Micro is actually notated with the mu. I know mu stands for the standard deviation of the population, but it also stands for micro as well. Plan is to do one sample t interval for mu. Which is obviously healing rate for in micrometers. So let's check for the randomness. Check. Do we have enough reason as to say that there's going to be more than 18 newts of these cuts made on the skin? Well, technically speaking, we really can't, but we have these measurements that's labeled here that's all going to be independent from one another. Or you can say that there's a good enough reason for us to assume that more than 180 newts are was new cells close a cut made in the skin of an anesthetized newt. There could be much more than 18 newts or 180 newts in this kind of scenario, basically. The last one, which is n is less than 30. So we're going to actually have to do a little bit of a dot plot there. So we can do from 10 to, I believe it was maybe about 40-ish. 40 is the last one, so 45. And we can do stat plot. So if I put all my here, ooh, boy. So if I just go to stand, oh, 19th was the nothing. So stat plot and then stat plot went on. And then on here, and then I can just try to make this into a dot plot, which is with this one. Actually, those are box and whiskers plots, so I can't really do a box and whiskers plots, unfortunately, here. All right, so if I had a TI Inspire, that would have been great. But from what I can tell is that this, I would have to just manually just try to do this. So 11, 12, 14, I think we have some couple of points here, 18 point here, and then what's next? 22, 23, 22, 23, 23. So we have a lot of 22s and 23s somewhere in the middle, 26, 27, 28, 29. We have a couple of 30s, 30s, 33, 34, 35s, and then 40. So we can see that it's going to be, when you put them all there, that it's going to be kind of a normal distributed curve. I mean, obviously, I just kind of rushed through this, but hopefully you guys actually have the dot plot, just kind of label it out and just don't spend too much time on drawing a dot plot, please. You got to make it quick and concise just to prove that it's normal. So we are going to go to do the stats, tests, t interval test. We have to do this one more time. One variable stats. Now we're going to calculate. And then when you go to tests, our mean and the standard deviations inputted nicely for us already. Our degree of freedom is 17 because it's 18 minus 1. And the sea level here would be 0.95. And so then that means that our interval is anywhere between, so due portion will be 19.171, 29.46, that we are 95% confident that the interval of the following captures the true mean of the mean healing rate in micrometers after an anesthetized newt. Okay. All right, so the next part is confidence interval about the difference in the mean. So when we have two samples, and obviously there's going to be two, the differences of the two, and how do we do it? Same thing. Randomness, 10%. Obviously, it needs to check for both of the populations there. And we need to check to see if they're both greater than 30. Now, if they're, for any reason, for each sample, the population distribution is unknown shape and it's less than 30, graph of the sample data shows no strong skewness or outlier. So it means that, the dot plot has to be roughly symmetrical or normal. All right, so let's say that I give you two samples like this and I ask you to figure it out. mu1 and mu2, true mean of monthly rent for all 1 bedroom, and mu2 being 2 bedroom. Check if the conditions for calculating a confidence interval for mu1 and minus mu2 are met. So do we have a randomness? Yes, check. Do we have 10%? Do you have enough reason as to believe that the monthly rents of 10 apartments of each type, is there more than 10 apartments of each type of 1 bedroom or 2 bedrooms? Absolutely. We have more than 100 apartments, I'm pretty sure, out there for each different types. We have less than 10, so we need to do the dot plot. And sorry, once again, I'm going to just kind of cheat my way through this and show you guys the dot plot that's provided for me as data. Notice how there's not much of a skew, not in one direction in particular. This one also, you can kind of make the point that this could be maybe bimodal in a way, but overall, not in general sense that it's going to show a strong skew in the left or right direction. So the sample size is small, but the dot plots don't show any outliers or strong skewness. As long as you have a good enough reason to believe that it's going to be normal or roughly symmetrical, please say so. So that is going to be for checking the conditions. This is another formula that I would like for you to write down. Yes, it's crazy, but it's pretty much the same thing as before. We subtract the means, and then it's T star times the standard deviation. But now, obviously, we have to add the variances together. So we have to square the whole thing, add them up, and then square root the whole thing. Remember, we have option 1 and option 2. Option 1 is using the formula, but option 2 is much faster. And I do strongly recommend to use option 2 because it saves you time. and just go straight on to the point. And it's totally 100% legitimate when you're going to be doing this on free response. All right, so we are still using the 1 or 2 bedroom sample, a size of 10. They give me these wonderful statistics right here. The sample mean and the standard deviation is the only thing that you should be looking at. And they ask you to construct the confidence interval with it. So we take the means and we subtract them. I believe that they are specifically asking you to go from 1 bedroom, mu1 minus mu2. In other case, we have sample 1 minus sample 2 here. That is the formula that we're going to be using. And then we have the t star value. Now, again, to determine this value, we always have to go to inverse t. I'm going to show you guys this once again. So if you guys go to second VARs, we go to inverse t. Now, what is the area for a 90% confidence? It's going to be 0.95. Now, why is that? 90% is in the middle. There should be 5% and 5%. We are talking about here. So that means that this all thing has to be added up, 0.95. Degree of freedom, well, both of them is going to be consisted of less than 10. So we're going to just press 9, press paste, and then you're going to get 1.833. That is going to be your t star value. And obviously, the standard deviations for sample 1 and sample 2, you can plug them in. And then eventually, you'll find this interval. So we have negative 148.591 to negative 7.409. Now, obviously, the rent for 1 bedroom apartment has to be smaller than the 2 bedroom. So it gives you a negative number for the interval. So these are all, again, option 1 to use technology, option 2 just use the formula. But I hope you guys can be flexible in doing both of the ways. If not, just rely on option 1. It's so much more so much easier, so much more comfortable to do it. Okay, all right. So we're going to go straight to a different example, and then I believe they're simply going to ask you to construct a 90% confidence interval, the difference between the mean, and blah 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 here. All right, so pause the video for me now, and then check your answers after, and then we'll pick it up from there. Okay, so what's lovely about this is that they actually don't really care about the fact that you type in the values into a table. Rather, they give me the sample size, and they give me the mean and the standard deviations right away. Now, unfortunate thing is that n is equal to 30. N has to be greater than 30 to prove actually central limit theorem. I know one of the things I said greater than equal to 30. My apologies. It always has to be greater than 30. So then means you have no choice but to actually kind of demonstrate the dot plots here. Oh, I'm sorry. Okay. All right, so what's lovely about this is that everything is provided for us. We have the sample, we have the mean, and the standard deviation. Remember, as long as the sample size is greater than or equal to 30, we can assume normality. So let's check. Do we have a randomness here for this? We have a random sample of 30, so that's a check as well. 10% of 30 trees from each half. Obviously, there's going to be more than 300 trees, so check. Independence for that is check. So for the state, what are we trying to test here? We're going to construct a confidence interval, and specifically, we are doing 90% confidence interval for 2 t sample, I would say. I think the specific 2 sample t interval. Yes, 2 sample t interval for mu. 1 minus mu2. In certain ways, I think we're just going to copy and paste pretty much for difference between the two means like this. So mu1 and minus mu2. And that is what we're going to say for just stating it out. And what is mu1 minus mu2 going to represent here? Well, they're going to represent the difference of the diameter at breast height in centimeters. So how the size of a long leaf pine trees in the northern and southern halves of the forest compare. And they measure the diameter at breast height. And here are the summary statistics. And basically, you're finding the difference between the two, the sizes of the long leaf pine trees in the northern and southern halves. And so based on the graph and the numerical summaries, write a few sentences comparing the sizes of long leaf pine trees in the two halves of the forest. So we have the mean of the southern ones to be much greater, but the standard deviation is actually a lot lower. So we have a less variability there. Northern ones, we have a mean that's a lot lower, but then the standard deviation is quite large. So there's much more spread. So I think to describe the sizes of the longleaf pine trees, you can talk about the shape, not really from the box and whisker plots as you see on the bottom half here, which is provided for you along with the questions, by the way. But mostly you should talk about the spread and where the center lies. So if you take a look at the answers, outliers, you guys all remember socks. Center, it appears that the trees in the southern half forest have larger diameters, blah, blah, blah. And then variability, obviously, is more variability for the northern longleaf pines. So I believe that should be how to describe those two. And then construct 90% confidence interval. This is what I was talking to you guys about. I've already stated for you guys. Plan, I've already done that for you guys. So let's go to the do portion. Now, this is much more interesting to do. Let's go to the stats. We're going to go to test. T interval. So we're going to do 2 sample T intervals now. So because we have now the mean of X1, which is 23.7, and standard deviation of 17.5, and a sample size of 30, 34.53, standard deviation, second one was 14.26, sample size still 30, confidence interval would be 0. I believe they said it was 90% confidence interval. Pooled, you can just say no to that and then just press calculate on that, and then here we go for the final answer. It seems like we're going to get this. All right, so we're going to go to t-test interval test here. So then we're going to go to 2 sample t-test. All the values, you're just going to copy and paste it right along here. For the pooled, tell yes, because for the pooled section, all right, so for this question that we have, after you type that in, what you're going to get is you're going to get an interval that is actually different from the answers. But because they phrased it I don't really agree with this, but negative 3.936. The only difference is that they declared mu1 and mu2 as a difference in the true mean between the southern to the northern trees. Well, we declared it as the first one being the north and the second one being the south. They said to find the difference between longleaf pine trees in the northern and southern halves. So north minus the south was what I was thinking. So you should get on negative numbers in that sense. They should have been a little bit more clear and as to which one comes first and which one goes second. And so I think U1 is a true mean of all trees in the southern half, true mean of all the trees in the northern half. So they said the order of subtraction when defining a parameter here, they didn't really specify that. So I would say that either way would totally do. But if you were to, let's say, swap up the order, you are going to get this number. But in a way, you can still conclude that this interval will capture the true difference between the northern pine trees. I think it was the captures the difference in the true mean of DBH of all the southern trees, of the northern trees to the southern trees in that way. So this is north minus south. But if you were to do south minus north, obviously you would get that interval. So that is where the discrepancy is coming from. Not a big deal. At the end of the day, you have to utilize this calculator correctly. And that's basically what it comes down to. All right, so these obviously tells you how to do it. Just you're going to use the calculator to do most of these things. The formula for the two sample t interval often leads to a calculation error by students. Also, the interval produced by technology is narrower. So as a result, your teacher may recommend using calculator two sample int to feature to compute the difference in the interval. Make sure that you name the procedure as this, not just mu1 and mu2. For the plan, and give the interval and the degree of freedom also in the do step. All right, so this is your checking for understanding. We have this question here. If you could just pause the video now and work on this. I really want to focus on how to construct a 95% confidence interval, and what does the interval in question suggest about whether the caffeine increases and things like that. So try to make this as mu1 and mu2, or in this case, I'm sorry, sample 1 and sample 2, subtract them and see the difference and that kind of thing. And so pause the video, plug it into the calculator, make sure you get those values, and we'll compare the answers. Okay, so I put in the data, and here's what the standard deviation was. We have 2.699, we have 2.624. And afterwards, what happens is that we are going to have to do state, plan, do, interpret. Sorry, I'm going to go through this super quickly, so please bear with me, but I'm just going to say it out loud. For state, you're going to construct a 95% confidence interval for the difference in true mean change in pulse rates for subjects like these who drink caffeine versus who drink no caffeine. So these measurement are the change in pulse rate. So change in pulse rates for mu1, pulse rate with caffeine, and mu2 would be the same thing without caffeine. So plan, we're going to the two sample t interval for mu1 minus mu2. So this exactly at the top, two sample t interval for mu1 minus mu2, just copy and paste that. And then randomness, do we have that? So do groups of 12, the first group of 12, and then all the measures. Okay, so 20 volunteered. So to take the part in the measurement, all the students measure the initial pulse rates. randomly assigned. So there's the word randomness there. So it's check. Do we have enough reasons to believe that there's more than 12 students here? Or I'm sorry, 10 students. Yes, check. So we have enough population for this. So assume independence. And the last one is, do we have big enough sample size? Well, no. So that means that we need to check for the normality there. So caffeine, we have 0 twice, 1 twice, 4, 5, 6, so 3, 4, 5, 6 in the middle, and then we have 8. So it's a little bit of a skewed distribution towards the right-hand side, because there's a lot more people onto the left, or maybe I'm not really plotting this correctly. Zeros, ones, we have a couple of 4s in the middle, and we have 5 and 6, 4, 5, 6. Oh, we have 1, 3 here, and then we have 8 here. Okay, now that you know, it's really hard to say, but it's more like this, and it's not really a strong skew. Like I said, it has to really super be obvious, and trust me when I say this, but most of the time it's just, you're going to say, you know, there's not a good enough reason for us to believe this is going to have an outlier or strong skew towards the one direction. So we're going to assume normality for this. Same thing here. If we just go to -1 twice, or -2, -1 twice, 1 here, 2 here, 4 twice, 5 twice, or there's 3. So again, that's assuming normality there. So I know that when n is less than 30, it's going to be a bit annoying to do, but please make sure you draw the dot plots and check for normality there. Then we're going to do the 2 tests, stat test, the 2 sample t interval, and we're going to put in stats here. So the mean is 3.2 for the first mean, and standard deviation 2.699, and sample size is 10. This one is 2.624, and the sample size is 10. And the confidence interval they asked me to do is 95. And then for pooled, please just press no. We're going to talk about that in chapter 11. Press calculate, and bam, there we go. So we have a degree of freedom. We need to write that down, 17.9857, with the interval -1.301, 3.701. So to interpret it, we are 95% confident that this interval will capture the true difference, the difference in the true mean of the pulse rate change in caffeine people versus non-caffeine people. Okay, so somewhere along those lines, I would like for you guys to have that written down. Make sure you check. And what does the interval in question 1 suggest about whether caffeine increases the pulse rate of subjects like these? Justify your answer. So it seems like, in more often than not, you know, we have much more the difference when you have caffeine minus the non-caffeinated people. The change in the pulse rate for caffeinated people are much higher. That's why it shows such a positive difference, and caffeine number is significantly greater than the non-caffeinated people in terms of the change in pulse rate. So about caffeine increases the average pulse rates of the subjects like these? Yes. So there's a good enough reason for us to justify that as part of our solutions there. Okay, so 0 is part of it, and -1.301 to 0, there's obviously certainly good portion of it, but from 0 to 3.7, I mean, you can see how much greater that is in terms of area. So yes, there's a good enough reason for us to believe that. I believe there's going to be more constructive answers for us to say forth, because they're going to give you some numbers to test or some things like that when we're doing these types of things. But for 2, you would just say yes, because we have a lot more positive difference here. Okay, so now we have this slide for comparing the 2 means. We have something called paired data. So for paired data, we have essentially for twin A's and twin B's IQ, high and income and low income family. So guys, I think for most, at this point, I'm going to stop. I believe that I still need to go over chapter 10 stuff with you in a little bit more in detail. And so when we get back to school, I will talk to you guys about t-test a little bit more, just to give you a little bit of an overview. But we'll start from a 2 means from a compared data, and as to how to find those things and what it really means. And yeah, so this video up until now, make sure you guys know how to do the t-test, how to find the confidence interval and those things. And when you guys come back, make sure you guys get ready for chapter 9 test. And so yeah, that should be it for this video. And thank you guys so much. I'll hope to speak to you guys soon.